All right, so what are we doing today? All right, well, here's what we're going to do. The Chapter 5 problem set number 3, which is on Moodle, of course. We'll do that today. In the other class, I didn't quite finish it, so I'm sure I won't finish it here either. But we'll get as much of it done as we can. So let me get that open, and we'll get started. Okay, so it's exactly what we've been doing the last few classes. Nothing surprising here. Everything's exactly what we've been doing. So let me just get it open. Oh, there's a lot of questions on here, but it's excellent, excellent practice. All right, I guess we'll just begin then. All right, hold on 1 second. Let me get this over here. All right, so in the beginning, we're just going to be looking at exponents. Now, in these cases, there's a couple of things we can do. There's a rule, of course, that we learned, the product rule, which tells us that if we have two exponents with a common base, we can just add the exponents when they're being multiplied together. So this one actually is equal to 3 to the 4 plus 2 power, or 3 to the 6th. Oops, 3 to the 6th. That's better. And 3 to the 6th, it turns out to be 729. And alternatively, if you want to, you could also just do this. You could just multiply 3 to the 4th, which is 81 times 9, and you'll get the same thing. Okay, so it doesn't specifically say that you must use the product rule, but you can if you want. If you would rather not, you can always feel free to just evaluate each term separately and then multiply them out. All right, every year somebody tells me that they prefer to do it that way, and that's fine. It doesn't say that you must use any particular rule. All right, now for this one, we'll have 5 to the 3 plus 3 power, 5 to the 6th, and that turns out to be, whoops, Jesus, hold on. Five to the 6th power equals 15,625. Or you can multiply them individually. 5 to the 3rd power is 125. So you'll end up with 125 times 125, or 15,625, same thing. All right, how about this one? By the way, if they don't have the same base, then this second approach is the only option that you have. We can only use the product rule because they have the same base. It doesn't always work out that way. But here, when it does, we may want to take advantage of it. So here, for example, the exponent is 4 plus 3, which is clearly 7. So we'll have 4 to the 7th. And that's going to give us 16,384. Or the other option we have is to multiply 4 to the 4th, which is 256, times 4 to the 3rd, which is 64. And if you multiply those out, you'll also get 16,384. So far, so good? All right. Now, by the time we're done here, you'll be the world's leading experts on exponents. That's for sure. All right. Now, how about this one? 2 to the 6th. Oops. Oh, plus 4 in the exponent. Nope. Let's see. Let's try that again. 6 plus 4 equals to the 10th. And 2 to the 10th turns out to be 1024. Okay, and again, as usual, there's another option, at least one, And so 2 to the 6th is 64, 2 to the 4th is 32. And if you multiply those out, of course, you'll get the same thing. Wait, no, sorry. This is not 32. This one is 16. That's better. Now it's going to be the same thing. If you multiply those together, 64 times 16, you should get the same thing, 1024. Beautiful. Now, these are division. Now, by the way, you have to read these carefully. If you notice, there's a slash hiding in there. I hope you noticed it. It may not be the most obvious thing in the world. So these are meant to be division problems. All right, so we'll be careful with those. Now, instead of using the product rule, we can use the quotient rule, which means you've actually got the exponent is not 4 plus 2. It's 4 minus 2. So it's 3 squared, which is 9, or else you can think of this as 3 to the 4th is 81 over 9, which is just 9. Beautiful. All right. So far, so good. Yes. How about this one? So if we use the quotient rule, it's 6 to the 5 minus 3, or 6 squared, which is clearly 36. Or if you use the other approach, 6 to the 5th equals 7,776. And you're dividing that by 6 to the 3rd, which is 216. And indeed, if you divide those, you will get 36. Okay. Here's an interesting one. 2 to the 5 minus 4 power equals, of course, 2 to the 1st, which is just 2. And of course, the alternative would have been to divide them directly. 2 to the 5th is 32 divided by 16, and you'll just get 2. Now here, I just want to point out that 8 is the same thing as 8 to the 1st power. So we can certainly apply our quotient rule here by doing the following. It's 8 raised to the 3 minus 1 power, which is 8 squared. Which is 64, or else you can just put in 8 to the 3rd power is 512, which is also 64. Beautiful. Now here we go. These are the so-called power rules, because look what's happening here. We're not adding these exponents, because 5 squared, the entire expression is raised to the 3rd power. This is actually 5 raised to the 2 times 3 power, which is 5 to the 6th. And that in turn is equal to 15,625. All right, or else you could just think of this as 25 to the 3rd power, which is 15,625. All right, so for the same reason, this is 4 raised to the 4 times 2 power. 4 to the 8th. And 4 to the 8th equals, 65,536. That's a big one. Now, if you do this directly, 4 to the 4th is 256. If you square 256, you'll get the same thing. In fact, it might even be good to do this as a double check. if you're not positive that you've done it correctly. You don't have to, of course, but you might want to think about it. All right, so what happens here? Oh, we're back to the product rule. We're going to have 3 to the 2 minus 4 power, or 3 squared, which is 9. Hold on. Or alternatively, you recognize that this is actually 9 divided by, now 3 to the minus 4th is 1 over 3 to the 4th, as you recall. I'll just make a little note here. One over 3 to the 4th which is 1 over 81. So what you've actually got here is, you could actually think of it as 9 times 1 over 81, or 9 over 81, which is just 1 over 9. Oh, wait a minute, what did I do? No, I screwed it up. Sorry, look, I just noticed it right here. This should have been, this exponent is minus 2. So this should have been 1 over 9. Or let's think of it as 1 over 3 squared. That's better. And now it's not 9, it's 1 over 9. And that's why this one will also be 1/9, because what you're actually doing is you're taking 3 squared, which is 9. 3 to the 4th is 1 over 81. And that's 1 over 9. Okay, now it's correct. All right, we're all set. Beautiful. Now, if you want to, I mean, you can write this out as a decimal too. But that's not absolutely necessary. By the way, I'm going to show you a cool little trick here. Suppose you went through all of this and you went to your calculator and you type 1 divided by 3 squared. Okay, on your calculator, you would put 1, and then you would put, let's get this out. Hold on one second. I'm going to get out my calculator and see how this one handles it. So in your calculator, you could put 1 divided by, you know, it's interesting. I just noticed it. Remember the traditional division sign that is on your calculator here? It's actually not on my keyboard. I don't see it. I guess they figured you'd use slashes, but if you're doing this on your calculator, you do need the division sign. Wow, this is very bizarre. There's some other symbols in here. Oh, option. Oh, this is a PC. Really? Would that, let me try if I can do the PC equivalent of that. Oh, it doesn't seem to understand what I'm doing. You know what? Well, I'll tell you what, let's do some research. How to create a traditional division. Oh, somebody else has got an idea. Oh, technology. It always lets you down at the worst. You do know this already. Even at your young age, you've already been let down by it enough times to know. It always lets you down when you need it the most. Okay, that is understood. All right. Or some knucklehead makes a bad decision. I mean, it's that simple. Oh my God. Now that's pretty scary that I have to go through all that crap. It says numlock alt 247. Well, it was so obvious, wasn't it? All right. Well, let's see what those imbeciles have done. If they've done this correctly. Numlock Alt 0247. No, it didn't work. I'll tell you what, there is a way this will work. I'll show you what this is. And then, oh, here we go. Some more advice. Good. All right, here we go. I'll show you how you might get this done. This actually does work. Jesus. All right, let me show you a technique that you might actually be able to put to good use yourself. Special characters. I don't know. I don't see that on here. Insert. This is a PC keyboard. No, there's nothing there. All right, let me show you my thought about this. All of the symbols that we see have had assigned to them a code. Watch this. All right, now watch this. Unicode is a code that is attached to every symbol, character, letter, you name it. OOF7. Watch what I'm going to do. And this is, remember, this is a PC. OOF7. If I hit Alt-X, look at that. It worked. Woohoo! So it's all about the Unicode. Now, again, this might not work on the Mac. I don't know, but it works here. It probably requires a different keystroke than Alt-X. Whatever's the Mac equivalent of Alt-X, that probably will do the job. So there's certain, yeah, it is cool. It's certain types of symbols. There is a symbol box in here somewhere. Watch this, insert symbols. And there's a lot of stuff in there, but it's all kind of jumbled together. And you're looking at it like, well, where am I going to find my division sign? La, 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 la. If I had all day, I could sit here and look for it. Look at this stuff they have. Where's my division sign? Well, that looks pretty cool. Ooh, no, we don't need that one, do we? No, let's get that out of there. Man, there's some wild stuff in here. There's even little pictures. Oh man, what is that? Fancy backwards N? All right, I don't know what that means. There's Greek letters. There's Roman letters. There's all kinds of stuff in here. Ooh, look at this one. Is that right? Oh my God, I never heard of that before. Huh. Well, that shows you how out of it I am with the technology loop. But you know, I'm kind of hanging in there. I'm only about 8 years behind the curve, I think. I used to be 20 years behind the curve. Now I'm down to 8. All right, I'm pretty proud of that. That's right. It's called progress. All right. Anyway, so because it's going to take me all day to find it, that's why. And if you look down here, you see where it says Unicode? That's what I just did. So in other words, if I needed, let's say for some reason, Lambda, right there it tells me the code is 03BB. So if I type 03BB and do Alt-X, voila, there's my Lambda. All right. Well, that was fun. Yes. Okay, so anyway. Yep, I'm getting there. And only 8 years to go, and I'll be all caught up. All right. So it's one, yeah, this is what I was trying to show you. If you do 1 divided by 3 squared, I'm going to do it right now on my keyboard here. 1 divided by 3 squared equals, and of course you can use the X squared button for this one. And then equals, it'll come up with 0.1111. Now, suppose you say to yourself, you know what, I'd rather write this as a fraction. If you hit the 1 over X key, which is way over in the extreme left-hand side. And what it'll do is it'll give you the inverse, and then it'll come up with 9. And this means that 0.111111 is 1/9. Okay. So if you're saying to yourself, oh, that's kind of annoying, all those ones, but that's actually, it's 1/9. Because, and you can tell by asking the calculator for 1 over x, which is the inverse. Now, it doesn't always work out like that. I mean, sometimes it'll be something that's not a nice fraction anyway, but it might help you with a case like this. Okay. Here, how could they get this off the keyboard? Does nobody use this thing anymore? There's some bizarre stuff on here that I think is less useful than that. Like, look at this thing. What is that doing there? Why do we need that? I think we should put the division. We should petition the keyboard manufacturers to put division back on the keyboard and get rid of that squiggly thing if they have to. Nobody needs this thing. And look what's underneath it. Look at that. Who uses that? No one. Alt. Right. Alt. That's right. Alt. Yes. So therefore, on a Mac, you should be able to put option / and that will give you this Unicode thing. All right, well, enough of that fun stuff. All right, let's get back to this. So the final answer is 1/9. That's the bottom line, because it's 3 to the 2 minus 4, 3 to the minus 2, or 1 over 3 squared. It's ultimately 1/9. Okay, very good. But remember that Unicode thing, you might need it. If you need a bizarre symbol, just look up on Google, what is the Unicode? And then you can insert it the way I showed you with Alt X, or in your case, maybe Option X. All right, what do we got going on here? We have 4. Now, this is also a product rule, rather. We've got -3 plus 5 equals 4 squared, which is just 16. Or else, now 1 over 4 cubed is 4 to the 3rd power is 64. So if you do it this way, you'll actually have 1/64 times 4 to the 5th, or 1024, and that is 16, yes. All right, now this one, same thing. It's a product rule. It's 5. The exponent is -3 minus 2. So you have to be careful with this one, with all the negatives. Okay. So what you could do is simply rewrite this as 1 over 5 to the 5th, which is 1 over 3125. And if you write it as a decimal, it'll be 0.00032. The other option would have been to put it as 1 over, now 5 cubed is 125 times 1 over 25. All right. Now, what about these? All right, same type of situation. You have 6 to the 3 minus 3. Oh, that's interesting, because we just end up with 6 to the 0 power, which is just 1. And this should come as no surprise, because look what you've actually got here. 6 to the 3rd power is 216. So yeah, you're just multiplying a number by its own inverse. All right, now this one is a quotient rule. You've got 2 to the 5 minus 7. 2 to the minus 2 power is 1 over 2 squared. which is 1 over 4, or 0.025. The other option would be to put 32 times 1 over to the 7th, which is 1/28. Ta-da! All right, so those are done. Okay, we survived those. Now we're ready for some scientific notation. So here's what we're trying to do. First things first, we always have to have a number with a single decimal before the digit. Digit before the decimal. 6.25 times 10. Now the question is, what exponent are we looking at here? Well, there's a few things we can do, but one way, which actually works, is to do this. If you had 6.25, how many places would you have to shift to get it to 6.25? In other words, let's see what we can do here. Let's try, if we started here, imagine there was a decimal point here. If I move to the right, 1, 2, 3, 4, 5, 6, 7, 8 places, then I will be right where I need to be. So this must be 10 to the 8th. Now, the other option is to say, well, you know, this is 625 million. A million is 10 to the 6th. 100 million is 10 to the 8th. Therefore, it must be 6.25 times 10 to the 8th. Now, suppose you decide to double check your results. Go to the calculator and type 6.25 EE8 equals. Now, I think we mentioned this once before. EE is shorthand notation for 10 raised to some power. So if you go into your calculator right now and type 6.25 EE8 equals, you will see that you do in fact have your original value. So we must have done it correctly. How do you like that? It's always good to be able to double check, especially with a calculator that saves you all this work. Who knew? Is anyone here use the EE button before this class started? I bet you didn't. In fact, some of you may not have even known that this calculator was on the phone. Did it catch your eye, or did you just go right to the fun ones when you got your phone for the first time? Yeah, you skipped over the serious apps and you just went right to the fun ones. It's okay to admit it. Yeah, like the camera and all this other nice stuff, and all these, like Instagram is here, and all kinds of fun stuff. There's Kindle, and mine has Kindle. What is Kindle? Does anyone know what Kindle is? Of course you do.
There was an app where you read books, so you can like.
It's for books, yes. This way you can have a million books with you at all times instead of having to lug them around with you, like in ancient times when you had to carry them with you, for God's sake, and they were on paper. And the thing about paper is you can't make the font bigger, can you? You can't make it brighter, can you? No. Okay, so anyway, on the other hand, when the internet goes down, you can read a physical book, can't you? So there you go. So you can never, I bet Moses wishes he had it. You can never completely rely on the technology. Let's just put it that way, because you know what it does? It always finds the worst possible time to let you down. Oh, it knows. All right, now what about this one? That's true. I agree with that completely. But in spite of that, and I do have physical books here, as you can see, I've got a few. Let's see. You can see it a little bit. That's the bookshelf back there. I have plenty of them, but you know what? It's just I don't want to have to carry them around with me. I know I love it too, but you know, the reality is it's just easier this way. All right. So what about this one? 9.910 times 10 raised to some power. Let's see what that power has to be. One, two, three, four, five, six. But let's double check. Type in your calculator 9.910 EE6 and see what it comes back with. And you'll see, let's see, where are we? 9.910 double E6 equals, yep, there it is. That's right. We like to double check. Now, here we're going the opposite direction. These are the small numbers. So you're going to have 7.3 times 10 to some negative power. How could you figure that one out? That's 3 places. Now, as a rule of thumb, just this helps me all the time. With small numbers, the number of leading zeros, which are the ones after the decimal point before we get to the first non-zero digit, is always one less the exponent. So here, for example, if we have 2 leading zeros, then that exponent has to be a 3. It's -3, but it's still a 3. Now, of course, we can double check. Type in 7.3 EE. Now we have to watch this one. With this calculator, negatives are expressed in the following way. You don't use the minus sign or subtraction sign. You've got this special key plus and minus, which is directly above the 8, and make sure that comes last. If you type in those numbers, 7.3 double E 3 negative equals, oh, don't forget the equals, and you'll get 0.0073. Beautiful. All right. How about this one? It's going to be 2.61 times 10 raised to some negative power, and that will be just the 1.
I have a question.
Yes, go ahead.
So I'm a little bit confused as to how you would decide like where you would move the decimal. Like for example, like it's 2.61, but how come like why wouldn't it be 26.1? I know that's like a stupid question, but I'm a bit confused.
No, because the convention is to only have 1 digit before the decimal point.
Oh, I see.
26.1, you would, it's not wrong, but the convention is to have exactly 1 digit before the decimal point.
Gotcha.
So,
okay.
Yeah, I mean, if you wrote a very deep scientific paper to be published and you made a mistake like that, it wouldn't look good. So just, it's just a convention that we all follow.
Gotcha.
Anyway, so again, let's double check this. 2.61 EE1 minus. And you'll see that, oh my God, it is absolutely, oh, don't forget the equal sign. It doesn't like that, because otherwise we won't know if you're finished. That's really what the problem is. 2.61 EE 1 negative. There, oh, wait a minute, what did I do? There we go, 0.261. Perfect. All right, now these will be a breeze. I'll tell you why, because all you have to do is type this into your calculator. But like for example here, if you type in your calculator 5.9 EE4, whoops, it'll just come right back. Let's see what it comes up with. 5.9 EE4 equals 59,000. And if you didn't want have, let's say you wanted to try it a different way, what you could do is do this kind of thing. Shift it to the right until you get 59,000. It took 4 places. And that's your double check. All right, so that's that one. Yeah, this is much easier, isn't it? Yes. So here we're going to have 6.28 EE6 equals. All right, so if you go to your calculator, 6.28 EE6, 6,280,000, which should not be a surprise because 10 to the 6th is a million. And so this must be some value in the millions. And then we've got just again 3.75 EE. Just make sure that you use this negative sign correctly. And don't forget the equal sign. And you should get 3.75 EE. Oh, wait a minute. No, sorry, I did it wrong. This 10 doesn't belong here. It's I messed it up. Sorry. It's the 10 is understood. It doesn't need that. There we go. And it's got 4 leading zeros. And then the 375. Okay. That's probably your safest bet. If you have a different calculator, of course, like you could just take 375 and use whatever function it has for exponentiation, raise it to the -5th power, and you'll have the same result. Okay, EE is unique to this calculator. In another calculator, just use y to the x or x to the y. And then finally, we have 9EE 10 negative equals. Now this one, you gotta be careful with it. There's 9 leading zeros. That's a lot of leading zeros to keep track of. Yes. See, now the unfortunate thing, with the larger numbers, you have commas that can separate the zeros. Here, we don't seem to have anything that can take the place of that. Although, I mean, if you're desperate, if you're really worried about it, you can put little spaces in here to help break it up a little bit. But it is 9 leading zeros. It's a lot of zeros. Now, here we are. We're going to do some algebra with our scientific notation. So remember, the strategy is to multiply out the constants first, and then apply the product rule to the exponents. All right, and in many of these cases, it turns out really nicely. In some cases, we have to make some adjustments. So like this one, for example, is just 6 times 10 to the 10th, and you're done. Now, by the way, if you wanted to double check this, you could actually do something like this in your calculator. You could put 3 EE4 times 2 EE6 equals. Why don't we try that and see what happens? 3 EE4 times 2 EE6 equals. Okay, oh, I see what the problem is. You know what? It works, but it's going to give you the actual number, which you then have to you need to turn it back into scientific notation anyway. So it's not as helpful as it looks. But, you can do that if you want to. Just to get an idea of what it's supposed to look like. All right, now, here's an interesting one, because we're going to have 5 times 8 times 10. The exponent here is 3 plus 5, of course. So you might say to yourself, all right, well, what's the problem? It's 40 times 10 to the 8th. But remember what we said a few minutes ago, by convention, you want one decimal or one digit in front of the decimal point. So how do we adjust this thing? I know what we'll do. Here's what we're going to do. We're going to divide the 40 by 10. But in order to avoid changing the value of this number, we're then going to have to multiply by 10. All right, so we divide the constant by 10 and then multiply the exponent, or the power of 10, let's say, to ensure that we do not change the value of this number. And then what ends up happening is that we end up with 4.0, and then we have times 10 not to the 8th but to the 9th. Okay, we're adding 1 to that exponent because we're multiplying it by 10. So while these are the same thing, 40 times 10 to the 8th is the same thing as 4 times 10 to the 9th. But remember, we prefer it to be written in the following way. All right, so did everyone get that? And so this will be necessary from time to time when you're dealing with these expressions. Okay. Now this one looks like we're going to have the same problem. So we have 6.2 times 4.3 times 10, and then the exponent is -2 minus 6. So we've got 6.2 times 4.3, 26.66 times 10 to the -8th. Now again, we have the same issue. 26.66 is not a single digit before the decimal point, is it? So what do we do about it? Since it's too large, we can divide by 10 and multiply by 10. Won't change anything, but it puts it in a more convenient format. So this becomes, now remember here, there's an implicit 1 here in the exponent. So our new exponent is actually -7. Okay. Pretty straightforward, but it's easy to make mistakes. That's why you might want to go through these steps. Just remind yourself what you're actually doing. What are you multiplying and what are you dividing? All right. Otherwise, it's very easy to make mistakes with this. Beautiful. All righty. Now let's try some of these. 1.7, 3.8 times 10, and the exponent now is, wow, look at this. So 1.7 times 3.8 is 6.46, so we don't have to worry about that. And then we have times 10 to the -11. Oops, -11. And that's all we need. I like that one. How about this one? Oh, this one looks very promising. And the exponent is 4 minus 7. (8.8) times 10 to the -3rd. And we're done. All right, let's see. In this case, 2.2, 3.6 times 10, and the exponent is 3 minus 4. All right, so when you multiply 2.2 times 3.6, you get 7.92, and the exponent is minus 1. Excellent. So now this one is 5 times 3 times 10 to the minus 2 minus 8. Fifth, uh-oh, you know what we're going to have to do here? I'm afraid so, yes. The 15 is too big. Not a problem because we know the trick. We're going to take that expression and we're going to first divide by 10 and then we're going to multiply by 10. So we'll just end up with 1.5 times 10 to the minus 9. Excellent. All right, let's see what's going on with this one. We've got 4.3 times 2.2 times 10, and the exponent is 5 minus 6. All right, 4.3 times 2.2 is 9.46. And then when you take 5 minus 1, you've got minus 1, and that's it. Oh, that was nice and easy. Here we go. Now these are divisions. And again, you have to watch out for these little slashes just in case they're not that obvious. Now the divisions sometimes are pretty straightforward. Sometimes they're not. So here's what I'm going to do. I'm going to use my very cool equation editor. Ooh, look at that baby. That can do a lot of stuff that you might not get elsewhere. Certainly the one that comes with Word is not this good. So basically what you're doing is you are dividing out the constants and then you're using the quotient rule on the exponents. So in other words, I have 2.0 because this is 5 over 2.5. Now the exponent is 10 to the 4 minus 2, which is 2.0 times 10 squared. And that's all you had to do. So again, don't forget, you're just basically treating the constants separately. That's where this 2 comes from. And then you apply the quotient rule to the 2 powers of 10. Beautiful. All right, and that's your final answer. So I'll do something similar right here. So this is now 9 times 10 to the 6th. 3 times 10 squared. So the ratio of 9 to 3 is clearly 3. And then we have 6 minus 2. And that's 3.0 times 10 to the 4th. Very good. Okay. What about this next one? So we've got a ratio. Okay, we have 4.2 times 10 to the minus 2. And then we'll have 7 times 10 to the minus 3. So the ratio of 4.2 over 0.7 is actually, or 7 rather, is 0.6. Here we have minus, now here we have to watch it because you're subtracting a negative number. And that's easy to mess up. So you end up with 0.6 times 10 to the positive 1. Because you're subtracting a negative number from the denominator. Now, there's just one problem. This is not set up properly. It is not, we do not have a single digit before the decimal point, a single non-zero digit before the decimal point. So what I'm going to do is this. I'm going to basically reverse what we were doing earlier. Instead of dividing and then multiplying, I'm going to multiply and then divide. Okay, so I'm going to multiply first, and then I'm going to divide. And that will get me where I want to be, which is 6.0 times 10. And it actually turns out, interestingly enough, to be 10 to the 0 power. Now, that's a very odd expression, but in terms of scientific notation, that is actually correct. But it is equal to just 6. All right, now let's try this one. What do we have? 6.4 times 10 to the 8th and 8 times 10 to the minus 2. All right, so the ratio of 6, you got the same thing here. 6.4 over 8 is 0.8, and we have 8 minus a minus 2, which is 0.8 times 10 to the 10th. But again, it's not exactly the way we want it. So what do we do about it? All right. Just like we did a few minutes ago, we're going to multiply by 0.10. And then divide by, multiply by 10 and then divide by 10. So watch.
I have a question. What's the reason for dividing by 10 again, and also 1/10?
Oh, because if you don't, you're going to change the value of this expression. If I multiply it by 10, in order to offset that, I need to divide by 10. Because I don't want to change the value of this
Gotcha.
expression, but I do want to write it in a different form. So if I leave out this divided by 10, I've actually got a completely different number. And that's,
Oh, I see. Okay. So the other question I had is which, like, for example, 1/10, is that always going to go on the right side of the
no.
is that always
Before
going
we
to go on
had
the right side of it?
no,
Right,
it
that's the thing,
depends.
because I noticed that.
Yeah. This time it's on the right because the number is too small. But up here we had a few cases where the number was too big. Like this one, it was too big.
That's
So
exactly. I noticed that.
So if the constant is too big, then you divide by 1/10, but then you have to multiply the power by 10. If the number is too small,
Gotcha.
it's the other way around.
Gotcha. Okay. Makes
And if
sense.
and if you're not sure if you did it correctly, again, you could just go right to your calculator and try them both. You could try 0.8 times 10 to the 10th with your calculator, and then try 8.0 times 10 to the 9th, and you'll see they both give you the same result.
hmm
That's how you know you didn't mess up this conversion. All right, and then there's one more, and then we can move on to sequences. All right, this stuff is fun, but sequences are maybe a little more fun. I don't know. That's a tough call. If we had a contest to determine who likes sequences better than scientific notation, I don't know who's going to win. All right. All right, 6.6 divided by 1.1. You see the exponents are 3 and 5. So this is going to be 6.0. And this will be 3 minus 5. So, oh, this was too easy. Where did this come from? It's just 6.0 times 10 to the minus 2. That one slipped through the cracks, that's for sure. But no, that's fine. That's all you need. Okay, very good. So now we're experts on exponents and we're experts on scientific notation. So now let's become experts on sequences. All right, now these are arithmetic, it says right here, these are arithmetic sequences. Let me move this down. And so what you're being given here is not the actual sequence, but the first term and the common difference. So it's a little bit trickier. And for each of these, we need to do two things. Oh, sorry, for each of these, we're going to do three things. The first 5 terms, the 12th term, and the sum of the 12 terms. So here's what we should do. Why don't we just start writing it out and see what it looks like. All right, so let's see. I've started with 1 and I've added 6. And those actually are the first 12 terms. So as far as the problem goes, in part A, you just need the first 5. Good. The 12th term, now here, what we need to do is use the formula. Okay, now we already know, by the way, I mean, of course we already know, you always have the option of just writing them out. But I'd like us to also get practice with the formula, because if you need to find a term that's really far into the sequence, you might save a lot of time by using the formula. So like if it wasn't the 12th term, but the 1200th term, then there's no way you want to write them all out. So use this formula and just confirm that the 12th term is in fact 67. Okay, so this means that A12 is, so A1 is 1, remember. We're looking for the 12th term, so N is 12. The common difference is 6. And it is in fact 67. And then for part C, we're looking for the sum of the first 12 terms. Now this you do not want to do manually if you can avoid it. That's why we have the special formula, which is S sub n equals the ratio of, oops, that's not what I wanted. N times, in parentheses, A1, whoops, that's not what I want either, plus AN all over 2. So the N is 12. The first term is 1. The 12th term is 67, which we discovered ourselves. And so you've actually got 12 times 68 over 2. And if you work that on your calculator, that turns out to be 408. And that's it for that one. Now, how about this one? Now, 38 is a little bit more straightforward because a common difference is 5, and that's always easy to deal with. There's just something about 5s and 10s. They're so nice, aren't they? Oh, yes. Yeah, good question. A1 is the first term. Oh, boy. In the sequence. So the subscript tells you which term we're talking about. Okay, so A12 is the 12th term, and D is the common difference between the terms. In other words, in this case, they're all separated by 6. All right, each time to go to one term to the next, we add 6. All right, nice. Now, oh, here we go. Yes, this one. The fun one, yes, there's something about 5s and 10s that are so natural. Why do you suppose the 5s and 10s make so much sense to us?
Fingers and toes.
To fingers and toes, that's right, 5s and 10s. That's right. That's the most natural number to us because that's how we, when you're a baby and you're learning how to count, that's how you did it with your fingers and eventually your toes when you got better at it. All right. Just think how weird the numbers would be if we had 3 fingers and toes. Ooh, then our number system would be very strange. That's right. We dodged a bullet there, let me tell you. All right, so the first one we need is the first 5. And then we need the 12th term. Now you can see already that it's 65, but let's use the formula. We said we want to know the formula as well as doing it out by hand. So A12 is 10 plus 12 minus 1, and this time the difference is 5. And indeed, it is 65. C, we need the sum of the first 12. And again, I think we can all agree that we should really use the formula for that. Although you can certainly feel free to do it yourself if you want to. I'm not going to stop you, but you might want to think about that one. All right, let's see. So what I'm going to do is rather than typing this all over again, I'm going to edit it. I only have to make 2 changes anyway. The first term was 10 rather, and the 12th term was 65. So we've got 12 times 75 over 2, which is 450. And that's it. That one's done. Good. Okay, now 39. Let's see what this one looks like. We have to watch it with this one because they're negative numbers. Not only are there negative numbers, but there's negative differences. All right, so again, I've kind of spoiled the surprise a little bit. You already know what the 12th term is, but that's okay. The first 5 terms are negative 9, negative 12, negative 15, negative 18, negative 21. Perfect. For part B, we'll use our formula to confirm that the 12th term is in fact negative 42. So the first term is negative 9, plus we have 12 minus 1, and the common difference is negative 3. Negative 9 plus 11 times negative 3. minus 42. That's exactly correct. And then for the sum, again, I'm just going to steal this formula here rather than typing it all over again. And so again, the nice thing about this is I really only have to change a couple of numbers anyway, which are the first term and the 12th term. So I've got 12 times negative 51 divided by 2, which is minus 306. And that's pretty wild. The sum is negative. But of course, that's because they're all negative numbers. Of course they are. All right. Now it looks like, what is there, one more? I think there's one more. And then it changes slightly. So let's run through this one. We start with negative 15, it becomes negative 17, negative 19. Let's see, how far out do I have to go with this one? That's the 12th one. So the first 5 terms are, as you can see, negative 15, negative 17, negative 19, negative 23. B, and even though we already know what the 12th term is, let's use the formula anyway. So we have A12 is the first term is negative 15. The difference is negative 2. Negative 37. What do you know? It's correct. All right. So all that remains is the sum. So let's check that out with our handy formula. Handy, I say. So again, we just really only have to change 2 numbers. All right, here we go. We've got negative 15 and negative 37. So here, oh boy, it's going to be almost the same. That's right, negative 312. That was just a coincidence. All right, now for the next group, it's a little different. You have the actual sequence, and what you have to do is come up, as usual, with the 12th term and the sum of the first 12. You don't have to, obviously there's no point asking for the first 5 terms because you already have them. But you do have to identify A1, which in this case is 5, and then D, in this case, is 8. And so what you might want to do, like we did before, is actually start writing them out until you find the 12th term, and then you can confirm. Let's see, is that 12? 1, 2, 3, 4, 5, 6, 7, 8, 9. It sure is. So the 12th term, but as usual, we'd like to use the formula if we can. Okay. We're getting pretty good at this. So A12 would have been 5 plus 12 minus 1. The common difference is 8. So that's 5 plus 88, 93. And then our sum is the same. The formula is the same. Except we have to change the first and last term right here in the parentheses. So we'll have 5 is the first and 93 is the last. Twelve times 98 over 2 is 588. Okay. So yeah, like I said, there's only two things this time. The sum of the first 12, I'm sorry, the 12th term, and then the sum of the first 12. All right. Now for this next one, we can see that A1 is 2 and D is 10. So if we continue to write out this sequence, there we go. So those are the first 12. And so therefore, let's try and apply this formula to prove that the 12th term is in fact 112. Two plus 12 minus 1 times 10 is 2 plus 11 times 10 equals 2 plus 110, 12. Great. And then for the sum, we just make two changes. We started with 2. The 12th term was 112. So we have 12 times 114 over 2, 684. Okay. Okay, now this one is interesting because it has a negative difference. It starts with 50, D is -2. So if you write this one out a little more, yep, that's the 12th term, but let's prove it with our formula. So A12 equals 50 plus 12 minus 1 times -2 equals 50 plus 11 times -2 equals 50 minus 22 equals 28. That's right. And then, of course, we need the sum of those first 12 terms. So the terms we need are 50 and 28. So we've got 12 times 78 over 2. And that turns out to be, let's see, 468. Now we're getting into some scary ones because you can see that we have fractions, but guess what? They don't all have the same denominator, do they? So we have to do something about that. Like what? Let's find a common denominator. So between all of these, the only fractions I see, or the only denominators, are 8 and 24. So let's do this. Let's rewrite this one. Let's do this on the side here. Oh, that works. Then we have 19 over 24, 35 over 24. Now 18 sevenths, 17 eighths rather, can be rewritten as 51 24ths. And then finally we have 67 24ths. And let's see if I can move these. Yeah, I'm running out of space here a little bit, but and I just want to get these out of the way. Okay, yes, so there it is. So I replaced 1/8 with 3 24ths and 17 eighths with 51 over 24. So now it should be clear that A1 is 3 over 24 and D is 16 out of 24. Before, it wasn't that obvious, was it? No, it wasn't the least bit obvious. So by changing these into, or giving them a common denominator, we made things a lot simpler for ourselves. Now, if I write this sequence out, like I've been doing, it's a little awkward, but we can manage it. And then we had 16 to this one to come up with 83 over 24, 99 over 24, 115 over 24. I think there's one more. Wait a minute. 1, 2, 3, 4, 5. Oh, we're not even close. That's the 9th term. Then we need 147 over 24, 163 over 24, and then finally, yeah, this is the 12th term. All right, so let's prove that with our formula, which is our favorite way of doing this. And, you know, again, we have to be a little careful because they're fractions. Okay. And so we've got A12 now A1 is 3 over 24 plus 12 times 1 times 16 24ths. So in a case like this, remember, here's a little side note here. 11 over times 16 over 24 is the same thing as 11 over 1 times 16 over 24. So we end up with 3 24ths plus 176 over 24. Ah, there it is. It worked out beautifully. 179 over 24 is indeed our 12th term. And that leaves us with this guy, the sum of the first 12. Again, it'll be a bit of a mess because of all the fractions. We can do it. So the two terms, A1 and A12, are 3 over 24 plus 179 over 24. Ooh, this is a mess. So we're going to have 12 times 182 over 24. Wow, what are we supposed to do with that? Let's find out. All right, so we start by multiplying 12 times 182. Wow, that's a big number. 2184. Now, here's where we have to watch it. I'm going to rewrite this as 2 over 1. And you might recall that dividing by a ratio like that is equivalent to multiplying by its inverse. So I end up with 2184 over 48. And it turns out that both of these are divisible by 24. So I can reduce this to 91 halves, which is 45 and a half if you want to write it out like this. Ooh, that was a mess, wasn't it? Oh, yes, it was. All right, now the last one is also a bunch of fractions, but these are easier to simplify. I think you'll agree. Like, you see what I mean? All we need is to convert the 1/2. So let's rewrite this as 5/10, 9/10, 13/10, 17/10, and finally 21/10. And then we'll carry on. But you can see that A1 is 5/10 and D is 4/10. So if I continue this sequence, I'll get 25/10, 29/10, 33/10, 37/10. Man, that's a lot of terms. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes. 49/10, which again we can find with our formula. And if we do that, we'll get, I'll just write it out by hand, I guess, because of all the fractions, A12. So we start out with 5/10 plus 12 minus 1 times 4/10. All right, so we're going to end up with 5/10 plus 44/10, 49/10. Okay, and then finally, at long last, we only have one step to go. That's the sum. Let's go grab that. So we started out, the first term was 5/10. Okay. Then we ended up with 49/10. So we're going to end up with 12 times 54/10. Okay. And where do we take it from here? A little simplification. So 12 times 54 is 648. Okay. 648 over 10 over 2. So I have 648 over 20, which is 324 over 10, or 162 over 5, which is approximately 32.4. Oh my God. All right, now this is where I left off with the other group. So we're not going to go any further because especially since look what's coming up, the geometric sequences, oh my God. And when those are done, we're going to have word problems, the dreaded word problems. Yeah. So these can definitely wait till Thursday. I think you'll agree. So that's good. So I'll tell you what I'll do. I'll post these incomplete solutions so you can look at them between now and Thursday. But what I would like you to do, of course, is carry on with these. And then on Thursday, when we're done with these, we'll just dive back into chapter 6. All right, so that should be enough for now. Are you all worn out? Yes. But on the other hand, it's kind of like warming up before, like, I don't know. Imagine that the rest of the day you're going to be lifting weights all day. Now you're all warmed up and ready to roll. You're intellectually warmed up for whatever comes this afternoon. So, all right, I guess I'll just see you all then on Thursday. All right, bye.
Bye. Thank you.
Thank you. Have a
See you
nice day.
later.
You
Thursday.
Thursday.
Bye.
Bye.
See you later.